Hello everyone, welcome to the second session on probability. So we'll be quickly looking at a recap of what we did in the first session. We looked at how probability is defined. It is defined as the likelihood of an event to occur. Then we looked at a couple of major properties of probability, one being that the value of probability always lies in the range of 0 to 1, including 0 and 1, which means a value of 0 means that that event cannot happen ever, and a value of 1 means that the event will always occur and there is no possible other outcome. And next we look at the sum of all the possible outcomes in the sample space of a given experiment is always equal to 1, which means if we add up all the probabilities of all the outcomes of a particular random experiment, then the sum of all the probabilities will always be 1. This is because obviously, like, if we are putting all the outcomes in front and there is no other outcome possible, then one of those outcomes have to occur, and therefore the sum of all the probabilities of all these outcomes have to be equal to 1. Then we looked at what are mutually exclusive events, for which we saw that since these events cannot happen together, the probability of intersection of these events is always equal to 0, where intersection means that it is the AND operator, which means the probability of both A and B to occur together. So this was regarding the mutually exclusive events. Then we looked at what is addition rule of probability, where we calculated the union probability for two events is equal to the sum of the individual probabilities, and then we subtract the intersection probability of the two events. So by union I mean the OR operator, which means at least one of A and B should occur. So this includes the case where both A and B are occurring, where exactly one of A and B, A or B are occurring. So we can have just A, we can have just B, or we can have both A and B here. And we add up the individual probabilities here and we subtract the intersection probability, which is the probability of both the events to occur. So this is how we define the addition rule of probability. Then moving on, we looked at what are independent events. So these were the events where the probability of one event occurring, given that the other event has already occurred, is still the probability of is still equal to the initial probability of that event. So for example, if we have two events A and B, then the probability of B given condition, so this vertical line here indicates condition that A has occurred. So A has already occurred. We are already given this particular condition and we are trying to find the probability of B occurring given that A has already occurred, and this in this case would be equal to the initial probability of B itself. So basically the probability in this case remains the same. So the probability remains same even after the given condition. And that is why we can say that B is independent of A in this particular case. Now whenever B is independent of A, we always have A is independent of B as well. So therefore, given that B has occurred, the probability of A also remains the same. Now moving on, we looked at what is the product rule for independent events. So just like we had for mutually exclusive events, the probability of A and B to occur together as 0, since mutually exclusive events are defined that way, that the two cannot happen together. In case of independent events, the definition changes for the intersection and it is defined as the product of their individual probabilities. So P A intersection B, which is A and B to occur, is the product of their individual probabilities. So remember, whenever we are using the addition rule, this particular rule, we need to make sure to have the correct value of A intersection B in the last term here. For independent events, it would be the product of the individual probabilities, while for mutually exclusive events, this value will go to 0. Yeah, so these were the major things which we saw in our previous session. Next, we'll be moving on to something called conditional probability. So we already got some introduction to it while we were looking at independent events, where we saw for independent events PB given A is equal to PB, which meant given that event A has already occurred, the probability of B was equal to probability of B. But this is only defined for the independent events. Now we might not have independent events, and we can have a given condition, and we should be able to calculate the probability of any event based on a given condition. So we'll be doing that using a particular example in this case. So we'll be looking at let us say we are looking at a particular bucket here where we have a lot of balls. Let us say we have 5 red balls and 5 blue balls. Now, based on this, we can calculate the probability of red ball. If we take out one ball randomly, so we define the experiment here, drawing one ball randomly. Now the probability of red in this case would be 5 upon 10, since 10 is the total number of balls and 5 of them are red. So obviously there will be a 1/2 probability of getting a red ball. Similarly, for blue also we'll have a 1/2 probability, since the number of blue balls is also 5 in the whole bucket in this case. Now if we have to define, or if we have to calculate R given B, in this case, what would it be? Given that a blue ball is drawn, we already know that R cannot be drawn. If it's a blue ball, it cannot be a red. So therefore, this conditional probability would be equal to 0, since if we have the blue ball already drawn, in this case, we cannot have a red ball since we are only drawing one ball. Therefore, this conditional probability in this case would be 0. Now moving ahead, let us say we draw. So let us say we draw a red ball, and therefore what we are left with? We are left with 4 red balls and 5 blue balls in the bucket now. Now what is the new probability of getting the red ball given that a red ball is already drawn? So let us say we call this R2 and we call this R1, where these particular numbers indicates the order of ball drawn. So by R1 we mean that the first ball was red, and by R2 we mean the second ball was red. Now since we are given here the first ball drawn was red, and after that we know that there are 4 red balls and 5 blue balls left. Therefore the probability of getting a red ball again would be equal to 4/9, because we are now left with only 9 balls. 4 plus 5, 9 total balls, out of which 4 are red balls. Therefore the probability of getting a red ball in the second draw, given that the first draw was a red ball, is equal to 4/9. Similarly, the probability of getting a blue ball in the second draw, given that the first ball was red, is equal to 5/9, because we still have 5 blue balls left out of total 9 balls. So this is how we define conditional probability. Now moving on, let us say we'll look at some more applications of this conditional probability, but let us say first we would like to cover another major topic here. These are marginal and joint probabilities. Now let us say we have a school where there are three classes, A, B and C, and in each of these classes we have either males students or female students. So we call male, female, and the number of students in each class, let us say we have 10 male students in A, 15 in B and 20 in C, while there are 20 female students in A, 15 in B and 10 in C. So there are in total we have 30 students in each of these three classrooms. Now let us say we select a student randomly from, let us say we select it from B, and we want to calculate what is the probability that the student selected from class B would be a male. So let us say we want to calculate the probability of getting a male student from class B. This will be what? This will be total number of male students in B divided by total students in B. Now the thing to note here is the given condition here is that we are drawing the student from class B. This given condition always goes in the denominator. Since our whole sample size itself has reduced now based on the given condition that we are only selecting from class B, therefore we have our base as 30 here, since that is the total number of students from which we are selecting a student here. Now the numerator says, since we are trying to find the probability of getting a male student, we want both the conditions to be met here. What are the number of male students in class B here? This will be equal to 15, and therefore we get our conditional probability here as 1 by 2. Now this is a conditional probability because we are given here that we are drawing from a class B, which acts like a condition in itself, and therefore the denominator here only has the number of students in class B. Now let us say we want to calculate a joint probability based on this particular table. So let us say joint probability is nothing but we look at probability of an event where both variables have a value. Have a specific value. So let us say we want to calculate the probability of getting a male student and he should be from class B. This can also be written as P M intersection B. So by intersection, like we saw in our previous session while we were defining the product rule, we saw that this is nothing but the AND operator. So this means the probability of getting a male student as well as he should be from class B. This is computed as total number of male in B divided by total number of students in total. So since we have no condition here that we are only drawing from B, we need to take the total number of students in this case, which will be nothing but 90, since we have to take the students from each of the three classes here. So whenever we are calculating a joint probability instead of a conditional probability, we always look at it from the total sample size perspective, which is equal to 90 in this case, and the total number of males in B is still 15, and therefore we get a required probability as 1 by 6. So why this is a joint probability? Because we are putting conditions on both the variables. The variables in these are, so we have two variables here, class and the gender. Since we need the class to be equal to B and gender to be equal to a male, Therefore, we are putting condition on both the variables here, and thus it is a joint probability in this case. Now, this is the major difference between the conditional and joint probability. Finally, let us move on to marginal probability. So, for marginal probability, we only look at value for one variable. So, instead of having a value for both the variables, we look at value for only one variable in this case. Now, let us say we want to calculate the probability of getting a male student. So in this case, we are not given any condition. Also, we are not given the value of the other variable at all. So the male student could be from any class. It does not necessarily need to be from class B. So what we do in this case is we add up all male students. So total number of male divided by total number of students. Now this is calculated as 10 plus 15 plus 20. So we are adding the male students from each of the three classes here, and we know that the total students still remains 90, and therefore this is 10, 25, 45 by 90, which is 1 by 2. So this is how we calculate the marginal probability here. Basically, marginal probability is nothing but probability of getting a particular value for a single variable instead of putting a value on both the variables like we had in joint probability. Now, similarly, we could also have calculated the marginal probability of getting a student from class B, which is nothing but 1 by 3, since there are equal number of students in each of the three classes. So the marginal probability in the first case PM, we saw that was the marginal probability for variable gender, where we are putting the value of M, and then for marginal probability based on the variable class, we are calculating the probability of getting a particular person from class B, which is 1 by 3, since there are equal number of students in each class. So these are the basic differences between conditional probability, joint probability, and marginal probability. Now we'll be moving on to more interesting stuff. We'll be looking at one of the famous questions of probability. This is something called Monty problem. So based on whatever concepts we have seen till now, one should be easily able to understand this kind of a problem. So the problem states that there are three doors. So let us say there are three doors which are indistinguishable, and let us say there's a prize behind one of this door, while there is no prize on the other two. Let us say, just for the sake of naming them, we call these doors as A, B, and C. And let us say now the game host, so there's a game host. He asks the contestant to select a particular door. Now let us say the contestant selects the door A. Now what the game host does is, after selection, game host opens a door which is different from selected door, that is A in this case, and shows there is no prize behind the open door. So once this particular contestant has selected the door, any random door basically the contestant can select. In this case he selects door A. The host, what he does is he opens another door which is not the one selected by the contestant and shows that there is no prize behind that door. So obviously in this case it would be the door C that would be opened, because he cannot open the door B since it already has a price behind it. So the game host would open the door C in this particular case, and then game host gives a choice to the contestant and asks him if he wants to switch his door from his earlier selection, and if the contestant switches his door, then the new door would be the one which will be the contestant's door, and if there's a prize behind the new door, then the contestant wins. And if there's no switch made, then he still sticks with his earlier door, which is A in this case, and in whatever the price is behind door A, that would be the price of contestant in that particular case. Now the question comes here: should the contestant switch the door? Now, even though in this particular example, whatever case I gave here, in this particular case, obviously if the contestant switches his door from A to B, the contestant would win the prize. But it is possible that initially the contestant could have selected the door B itself. Then in that case, the contestant, if he would have switched, he would not have won the prize. So what we do here, we don't make estimations. We look at exact calculations using probability and see what is the exact probability of whether the contestant would win if he switches versus if he does not switch in this particular case. So let us say, since we initially don't know whether there's a prize between, we don't know which door will have the prize. So what we do is, let us say we assume that we select, so this is selected door A, and we assume that prize is behind door B. So prize door. So let us say we call this B, and in this case, if there is a switch made, then what is the win probability? This win probability in this case would be 1, because in this case the game host would have opened the door C and we would have won if we would have switched to door B. Now let us say if the selected door was B itself and the price still remains the same, let us say it is door B, and in this case the host would have shown one of the two doors, A or C, and would have then asked, so let us say host shows door A and tells you that there is no price behind door A, as you can see, and since you have selected door B initially, he asks you whether you want to switch the door to C or not. So now in this case, if you switch to C, you would obviously lose, and therefore there is a 0 probability of winning in this particular case where you are switching. Now let us say if we would have selected door C initially, then host would have definitely shown you door A, which doesn't have a price behind that, and he would have again asked you whether you want to switch to door B or you want to stay with your door C. And in this case, if the switch was made, the winning probability would have been 1. Now, since initially we don't know what is the door behind which there is a price, all these three possibilities are equally likely. So the probability of winning in case we switch the door is actually 2 by 3. So it is actually recommended in the Monty Hall problem to switch the door, because your probability increases to 2 by 3, which was initially supposed to be 1 by 3, because the price could have been behind any one of these three doors. But why the probability increased here? Because there was an extra information. So there's an extra information in a way given by the game host. This acts like a condition based on which this probability increases. So since we know that the game host will always open the door which doesn't have a price behind it, therefore we are very sure about that in all these three cases, and therefore we can estimate that in two of these three cases we are actually winning if we switch the door, and thus one should switch the door when the game host gives that particular choice. So this is how the Monte Carlo problem works, and there could be many variations to this problem, but we have looked at the very basic case here, and the answer to it is we should always switch whenever the game host asks us, because we have a 2/3 probability in that case for winning the prize. So this is all from second session. In the next session, we'll be looking at some more interesting problems related to probability, but I think we have looked at most of the basic concepts of probability have already been covered in these two sessions, and wait for more interesting stuff. Thank you.